Good morning. Sorry. No problem. So we can start. And we are going to start with Ignacio, that he's going to talk us about Herbigs and the creation in the Herbigs.
Okay, so thanks, Rebecca, and thanks, Vladimir, and the organizers for inviting me to give this talk. Vladimir asked me to talk about accretion rates in Herbig Ae stars, and I have focused the talk on how we measure stellar accretion rates from the observations. So the first question is, why should we care about accretion? There are several reasons here. One could be that we are used to understand young stellar evolution from the evolution of the dust, from the evolution of the spectral energy distribution. So the typical evolution from class 0 to class 2 from Lara et al. But there is an alternative way, which is to understand this evolution from the accretion rate decline. You have seen this plot yesterday. It's a classical one from Hartmann. It refers to classical T Tauri stars. And in principle, this is derived from a combination of theory and observations. So we know that at the very beginning, at the class 0, class 1 stages, we have very high accretion rates. It is not clear whether all objects or some of them experience this theory outburst. But in any case, there is a decline in the mass accretion rate until the envelopes dissipate and we reach the optically visible premium sequence phase, the class 2 phase. So this is this region where I will be focused on. During the class 2 phase, we have a more or less a steady mass accretion rate, and then the disk dissipates, and finally we have a negligible accretion rate. And actually, the mass accretion rate, the accretion rate is a probe of the atomic gas that goes from the inner disk to the central star. So it's an alternative. If one knows the accretion rate and has some knowledge about the accretion evolution, one can infer a value for the disk mass, which, as you know, is a very important parameter, but it is still very difficult to constrain because of the many uncertainties involved. So there are ways to derive the disk mass from the, at least a lower limit of the disk mass from the mass accretion rate. It's obviously a very important parameter for many modelers for detailed modeling of the disk. And perhaps the most interesting is that we do not have direct access to the mass accretion rate, which means that even being an observational astronomer, I need an underlying physical model in order to translate from observations to mass accretion rates. So in other words, inferring the mass accretion rate requires understanding the physics of the star-disk interface. So then the question is, does the same model that is valid for the T Tauri stars is also valid for the Herbig Ae stars? Does magnetospheric accretion also work in these objects? So this is the classical scheme that you have seen many times. So according to magnetospheric accretion, we know that the disk does not reach the stellar surface, but is truncated at some point by magnetic field lines. So the material is channeled through these magnetic lines until it reaches the stellar surface, generating hot accretion shocks. So obviously, the main requirement that we need to drive magnetospheric accretion is a magnetic field. But the question is how strong this magnetic field should be in order to drive magnetospheric accretion. So if one goes to the classical formula by Gaussian, Lamb, and Xu et al., or the ones that are summarized here by John Skrull et al., one sees that the magnetic field that required to drive magnetospheric accretion depends on the mass accretion rate and several other parameters, stellar parameters. So if one plugs in the typical parameters for a T Tauri star, one sees that we need a kilogauss magnetic field, which is actually what is measured for T Tauri stars. In the case of the Herbig Ae stars, if one plugs in the typical values for a Herbig Ae star and taking into account the large stellar radius and rotational velocities that these objects have, we reach the conclusion that we do not need kilogauss magnetic field. It could be enough with much smaller magnetic fields. So yeah, it's true that typically Herbig Ae stars do not show kilogauss magnetic fields, but they do not need kilogauss magnetic field to drive magnetospheric accretion. In turn, a small magnetic field translates into a small truncation radius. So this is the scheme. For a large magnetic field, we have a large magnetosphere, and as the magnetic field decreases, the magnetosphere decreases as well. And eventually, if we have no magnetic field at all, then we change the mode. We pass from magnetospheric accretion to direct boundary layer accretion. So does magnetospheric accretion also work in Herbig Ae stars? I don't know, but I will show several evidences that may suggest that it could work for Herbig Ae stars, but probably not for Herbig Ae stars. And actually, the earliest suggestions indicating that magnetospheric accretion could work in Herbig Ae stars were given at the beginning of the century, mainly from spatially resolved observations from spectropolarimetry by Bink et al. And interferometry by Eisner et al. The first proper magnetospheric accretion characterization of Herbig Ae stars was made by Muserol et al. In 2004. And the object that they selected to make this study was precisely UX Ori. So this is a very detailed study. And there they used the magnetospheric accretion line modeling that were previously used for T-tauri stars in order to reproduce several line profiles of this object. But they also provided an alternative method, which is the measurement of the excess in the near V part of the spectrum, in particular in the so-called Balmer excess. So from magnetospheric accretion shock modeling, they could translate this observed Balmer excess into a given mass accretion rate. So this was a seminal paper because this allowed us and several others to infer accretion rates from the Balmer excess. So here is what I was talking about. I don't know if you can see this, which is the naked photosphere in gray. And here is the observed spectrum. So the difference is this excess is the Balmer excess. So from magnetospheric accretion shock modeling, we can translate this Balmer excess into a mass accretion rate. A main difference of our work with respect to others is that we consider that this transformation between Balmer excess and mass accretion rate is strongly dependent on the stellar parameters. So basically, the same Balmer excess translates into a different accretion rate depending on the stellar mass, the stellar temperature, and the radius. So here are several examples with different colors, different types of lines, just to show this dependence. So from this, we derive the accretion rate for 38 northern Herbig Ae stars. Accuracy that one can reach from this methodology is typically less than half an order of magnitude. And once these accretion rates were derived, we compared the accretion luminosities with the luminosities of several emission lines that we had at that time, from the spectra that we had at that time. So basically, we compared with the H-alpha luminosity, the oxygen forbidden line luminosity, and the bracket gamma luminosity. And we found that the correlation that was typically used for T-tauri stars is also valid for the Herbig Ae stars, which is good news because it allows us to derive accretion rates in a more rapid manner. Although, due to the scatter, the accuracy that one can reach through this methodology is a bit smaller. So accretion rates are valid within 1 order of magnitude or so. I'm talking about how to measure accretion rates in Herbig Ae stars, so I would like to mention also how to not measure accretion rates in these objects. The first one is this parameter, the H-alpha, the width of the H-alpha line at 10% maximum intensity. This is a very common parameter that has been used in T-tauri stars. Nata et al. Demonstrated that there is a correlation between the width of the H-alpha line and the mass accretion rate, but when we put the Herbig Ae stars, the correlation breaks. The reason is that most Herbig Ae stars have large projected rotational velocities, and these rotational velocities affect the width of the H-alpha line, regardless of the accretion rate. Similarly, for T-tauri stars, we know that the accretion rates can be measured from the photospheric line veiling, but this is not the case for Herbig Ae stars. Most of the Herbig Ae stars do not show photospheric veiling. As Muserol et al. Explained, the reason is that the temperature of the accretion shocks is very similar to the temperature of the stellar surface. So this contrast effect is not observed in the Herbig Ae stars. And another point I wanted to to clarify is that we have just seen that there is a correlation between accretion rates and line luminosity, which is useful to derive typical accretion rates, but one should be very careful when trying to derive accretion variability from the variations of the line luminosities. And the reason is that we see that the variations in the Balmer excess are decoupled from the variations of H-alpha and many other lines. So these are a couple of examples. R tau, for example, we saw that the Balmer excess increased, meaning that the accretion rate increased, and at the same time, the H-alpha luminosity decreased. There is another example here, but the point is that this is very common to be observed. We see variations in the Balmer excess and in the different lines that, and these variations are not coupled. This could be because different lines, different emission lines are affected by different physical processes apart from accretion, or could also be that there is a time delay between the moment that the material accretes onto the star and the moment when this accretion shock reaches the different part of the disk where the different lines originate. There is a very interesting paper dealing with this time delay by Dupré et al. So more recent accretion estimates, Fairlane et al. Derive accretion rates for 91 southern Herbig Ae stars, again, by modeling the observed Balmer excess. In this case, we have X-shooter spectra, so we were able to derive the stellar parameters that are necessary to derive accretion rates. And the thing is that here we could compare the accretion rates that we derive from the Balmer excess with the luminosities of all emission lines that are covered by X-shooter, which means from the near infrared, the near V, through the optical, through the near infrared. And we paired this with the previous correlations that were derived by Alcalá et al., similar X-shooter data for T Tauris. And you can see that these correlations hold both for T Tauris and Herbig Ae in a very similar way, which again is good news because one can choose the favorite line, the favorite emission line, use these type of correlations and derive accretion luminosity with an accuracy of one order of magnitudes. But I find this type of correlation very curious because this is telling us that all emission lines can be used to estimate accretion rates, but at the same time we know that not all emission lines only probe accretion. So I have mentioned before that that the accretion variability from the Balmer excess is decoupled from the simultaneous spectral line variations, which could be due to this time delay. We know, it has been mentioned before by Larissa and Rebecca in previous talk, that the main bracket gamma and H-alpha emitting regions are larger than the accreting region in many Herbig Ae stars, but still we can argue that the H-alpha and bracket gamma are tracing winds, and winds are accretion powered, and that could explain why H-alpha and bracket gamma correlate with the accretion luminosity. But we also know that there are some other emission lines, for example, the oxygen forbidden line, that in principle is not related to accretion. So this line, the oxygen forbidden line in the optical, is explained from the surface layers of the disk, very far away from the accretion region. And still, we see that there is a correlation between this line and the accretion luminosity. So this motivated us to do this paper, trying to explain why we see correlation between the accretion luminosity and every single emission line. And the explanation that we give is basically a mathematical consequence of the underlying correlation that exists between the accretion luminosity and the stellar luminosity. I don't want to enter into details. You can have a look through this paper if you're interested. The point here for this talk is that, okay, we can measure accretion rates from the line luminosities, but we can also use this correlation to derive accretion luminosities from the stellar luminosity. And the scatter and the accuracy is practically the same, one order of magnitude. Okay, so present. Gaia, of course. Gaia is providing us with lots of distances, which means that we can redetermine the stellar parameters for all the Herbig Ae stars. The stellar parameters are fundamental to derive accretion rates. This is actually what Miguel has done. So now we know the stellar parameters for more than 200 Herbig Ae stars. Accretion rates, new accretion rates are being provided, for example, by Arun et al. We have accretion rates for 106 Herbig Ae stars from the H-alpha luminosity, and this is increasing. You can have a look to poster 10 by Wichitanakom et al. And this is not related to the talk, but I just wanted to point out that it has been mentioned by Miguel and others that the situation for the Herbig Ae regime is not the same as for T-Tauri stars. So, people that study T-Tauri stars, they can look for a given star-forming region, they can count all the T-Tauri stars they have, they can go then to a different star-forming region, and they know how many T-Tauri stars they are, and they can make some sort of evolutionary studies. In our case, we know that the Herbig Ae stars are random and selected in all the sky. But the good news is that they are not completely random in the sense that they are physically representatives in terms of that they reproduce the initial mass function. So the ratio between Herbig Ae stars that we know and the Herbig B stars that we know is physically consistent in terms of this initial mass function. Okay, so far I've been focused on the accretion rates determined from the magnetospheric accretion scenario. That we can do that we can infer accretion rates from magnetospheric accretion does not mean that magnetospheric accretion is the actual model that works in Herbig Ae stars. Although there are other lines of evidence that suggest that magnetospheric accretion could work in Herbig Ae stars. This does not aim to be complete, but just to mention several lines of evidence or several approaches that have been used to support that this magnetospheric accretion model could work in Herbig Ae stars. It is more difficult to find papers that clearly claim that magnetospheric accretion is not working in Herbig Ae stars. There are a few here. I don't want to enter into the debate, but I want to mention this very interesting paper by Blondel and Thénardier, because in this paper they derive accretion rates for F and A stars, assuming the boundary layer scenario. So they didn't discuss if magnetospheric accretion is valid or not. They simply took the boundary layer scenario and derived accretion rates for a sample of Herbig Ae stars. So I was wondering, what if our magnetospheric accretion estimates are wrong? How wrong could we be? So in this plot I have plotted the boundary layer measurements from Blondel and Thénardier versus the magnetospheric accretion estimates from our papers. I have chosen the best case scenario, meaning that within errors in our papers and in the Blondel and Thénardier papers, I tried to make them as close as possible. So in this best case scenario, the magnetospheric accretion and boundary layer estimates of Herbig Ae stars differ by less than 1 order of magnitude in most of cases, although there are obviously outliers. In general, if we are not that conservative, the accretion rates determined from boundary layer tend to be larger than the accretion rates determined from magnetospheric accretion, and can be by more than an order of magnitude. And this, of course, could have consequences in many aspects, for example, on the disk dissipation timescales. Okay, I haven't mentioned that, there are many works that support that magnetospheric accretion could work in Herbig Ae stars, but at the same time, many of these works also show the many differences that are between Herbig Ae and Herbig B stars. And many suggest that there could be a change in the accretion scenario precisely at some point in between the Herbig Ae and Herbig B regime. And actually, when we measured when we tried to reproduce the Balmer excesses of the Herbig Ae stars, we found a subsample of objects that showed such a huge Balmer excess that was impossible to fit from the magnetospheric accretion shock modeling. The reason is basically that we needed that the stellar surface is covered by more than 100% through the accretion shocks, which is obviously impossible. And it turns out that the vast majority of this subsample of Herbigs that cannot be fitted through magnetospheric accretion are Herbig B stars. So definitely we need an alternative. Perhaps boundary layer, I don't know. And I want to finish with a couple of things, some work in progress. Now we are focusing on these non-magnetospheric Herbig B stars, the ones that we cannot fit through magnetospheric accretion. The first thing that we want to do is to have a closer look to these sources. So basically we have gravity data for the six brighter non-magnetospheric Herbig Ae stars. This is very preliminary. Just the other day I saw this preliminary data reduction, but it's just to show that there are some spectrointerferometric signals. So the goal is just to compare how these objects behave compared to the previous data we have with amber or with gravity for Herbig Ae stars. And another thing is that we want to modify the initial models that were applied for Theta stars when the boundary layer model was the actual model valid for Theta stars before the magnetospheric accretion, and we want to modify those boundary layer models in order to apply them for the Herbig Ae stars. And it could be interesting, especially if we add UV data, not only the near UV, because as you can see here for this Herbig Ae star, magnetospheric accretion is capable of reproducing this near UV excess, forcing it a lot. I mean, this needs 99% of the stellar surface covered by accretion shocks, which is not very realistic. But at the same time, it cannot reproduce the UV, the far UV. But whereas boundary layer could, in principle, reproduce both the near UV and the far UV. So this looks something promising, and for that we need additional UV data from several telescopes. So conclusions, magnetospheric accretion is not a direct observation. We need an underlying physical assumption to translate from observations to mass accretion rates. There are numerous indications suggesting that magnetospheric accretion could be valid for Herbig Aes and some Herbig Ae stars, although, of course, there is not a consensus. The typical magnetospheric accretion estimates provide 10 to the minus 7 solar masses per year, although this increases with the stellar mass as for the T Tauris. The accuracy of these measurements depends, of course, on the methodology used. If we use direct estimates, the near UV excess, the accuracy can be smaller than half an order of magnitude. The accuracy is worse if we use indirect measurements, the correlations with the emission lines or with the stellar luminosity. I haven't talked too much about the emission line modeling. Larissa talked the other day. This is, of course, very important to test if magnetospheric accretion is capable of reproducing these line profiles. But concerning the topic of this talk, how to measure accretion rates, this methodology is less robust in the sense that it depends on several relatively free parameters. There are not many boundary layer estimates for Herbig Ae stars, but the ones that are there suggest that if accretion goes through a boundary layer, then the accretion rates that we have now are lower limits to the real ones. And definitely we need alternatives to reproduce the near UV excess of several Herbig Ae stars. Magnetospheric accretion doesn't work for them. It could be boundary layer, it could be a different accretion scenario, not boundary layer or magnetospheric accretion. It could be winds. In any case, this is an open problem. And with this, I finish. Thank you.
Thanks, Ignacio. So questions?
We know that there is a correlation between the mass accretion rate and the stellar mass for the T Tauri stars with a power index about -2. Different people provide different power indexes. Could you tell something about the Herbig stars? Is there such a correlation? And if there is, then what is the power index? Is it shallower or what?
Is it what, sir?
Shallower or? Shallower.
Yeah. So, yeah, definitely there is a correlation between mass accretion rate and stellar mass. Actually, I showed a correlation between accretion luminosity and stellar luminosity, which is basically the same correlation. Regarding the slope, you can talk with Chumpong Wichitanacom. He has a poster there, and there is a paper about to be submitted. We find that the slope is basically the same for the Herbig Ae stars and the T Tauri stars, but there is a change of a slope for the Herbig Ae stars. Another thing is how to interpret that. But yeah, the correlation is there, and basically it's the same slope for the Herbig Ae stars.
Do you have a simple explanation of why it seems to me from the example you showed that the boundary layer predict the excess is bluer? I mean, you have much more in the UV, far UV than you have from a magnetospheric accretion model, which is basically a shock model.
Yeah, here. Yeah. So basically, so basically, in the magnetospheric accretion model, well, there are several parameters, but the parameters that control everything is the filling factor, the fraction of the stellar substrate that is covered, and the temperature of the accretion shock. So the temperature of the accretion shock makes the contribution to go up and down, and the filling that, yeah.
And also steeper, flatter.
It could be steeper, but mainly controls how up and down this, the accretion contribution goes, and the filling factor goes like this. In the case of the boundary layer, we have additional parameters, which of course there are 3 parameters, and that's basically we have the size of the boundary layer, okay, which is the region where the angular rotational velocity decreases very fast, and the inclination is also important, and also the temperature of the boundary layer. So by combining these 3 parameters, and especially by changing this size, we can make the contribution from accretion to be brighter in the near V. We can talk about the specific formulas. I have the.
Questions? Yeah. You? Oh, sorry.
So I have a question about maybe you have some estimates of gravitation radius and magnetic fields for some stars that are non-magnetic corrector in your talk.
You refer to this first. Yeah, so regarding the gravitation radius, when we estimated accretion rates here, what we used was the projected rotational velocities of the stars. So basically, we could derive the gravitation radius, and we put that limit in order to make these fits, which is typically for a Herbig Ae star. For a theta star, it's typically use 5 stellar radius, and for a Herbig Ae star, it could be like 2 solar radius or so. But if you mean
for non-magnetic accretion stars, what are the values of gravitation radius?
I don't know, and actually that's a good exercise. Yesterday I was having a look to the magnetic fields of Herbig Ae stars, and I think it would be interesting to make this exercise for all the Herbig Ae stars. We know the stellar parameters for all of them, so we know what is the magnetic field required. Again, if you put the typical values, it's 100 Gauss, or it could be even less, and then compared to the magnetic fields of the measured. But it's to me, that I am not an expert on magnetic fields, is really difficult. There are different works. Some of them say report magnetic fields that are very different from the other, and even in the same work, applying different methodologies, the magnetic field can change almost by an order of magnitude. So I'm not really sure. I would need help to infer that.
And I actually have another question. Can you move to the slide where you have a spectrum of boundary layer and magnetic accretion? I see that the magnetic accretion actually explains pretty good the long wavelengths, and the boundary layer explains short. Maybe there's some kind of intermediate case, like some part of gas are going through the magnetospheric accretion, and some part of gas are ignoring the magnetic field because the gas is not completely ionized. Can it be something like that?
Yeah, I mean, there could be many possibilities. I mentioned this paper here, which is a very interesting one. I mean, it's a really complicated, to me, very theoretical model, but it's something in between magnetospheric accretion and boundary layer. And yeah, perhaps there are other intermediate scenarios that could fit the observations. I don't know.
I am very skeptical about this Balmer jump, to use Balmer jump as an indicator of accretion. I mean, in your plot, I see accretion rate up to 10 minus 3.
Where?
Solar mass per year, or 10 minus 5. Oh.
That's the accretion luminosity.
Yeah.
No. Yeah, this one. 10 minus 4, you see? Yeah.
Yeah, well, one object, and I have to say that in this case, I mean, for the Herbig Ae stars.
Okay, 10 minus 5. 10 minus, okay, 10 minus 5. So in fact, at such accretion rates, gas density, if it's not 100% of the stellar surface accretion spot, and it should not be, otherwise you will have boundary layer, in fact. So in this case, density would be so high that pre-shock region would be optically thick. And in fact, it means that then you will have the spectrum of effective, of the star with effective temperature equal to effective temperature of the shock. I mean, density to V in cube divided to 2. So this is huge density. It should be optically thick. And as I know, nobody calculates such things. So just here we have on the computer, Dodin calculate this for 10 minus 7 accretion rate and filling factor 5%. So in this case, summary spectrum, the star plus accretion shock is practically the star. So, and if you will have 2 order magnitudes larger, then you will have photosphere above the shock. You will not see the shock. So,
Okay, so 2 things here. First, the median or the mean accretion rates that we derive for Herbig Ae stars, and now we are talking about hundreds of Herbig Ae stars, is 10 to the minus 7 solar masses per year with variation, but that's the typical value. Another thing is that in this particular paper, the initial one, we couldn't derive accretion rates for the Herbig Ae stars because of the reasons that I explained, that the Balmer excess was that huge that could not be fitted through. What we did, just to provide some accretion rate, but we were very careful and said, do not trust, I mean, this is the only thing that we can do, is that we use the correlation with H alpha, and from that correlation we estimated the value that could be, but the reality is that we do not know the accretion rates for the Herbig Ae stars. In any case, if you do not trust the magnetospheric accretion way, or the Balmer excess way, which is a typical thing that has been used both for T-Tauri stars and Herbig Ae stars, the alternative is even worse. I mean, as I have shown, the boundary layer predictions, both for T-Tauri stars and Herbig Ae stars, are even larger. I mean, the accretion rates are even larger. So I will be very cautious with these very high accretion rates because they refer to early type Herbig Ae stars, and we don't know the accretion rate. But normally, the accretion rate that we derive is 10 to the minus 7 solar masses per year, which I think is more.
discuss later.
Okay.
So thanks, Ignacio, again.